Okay, let's get started. Good morning, everyone. Welcome back. I hope you had wonderful Chuseok holiday. So last time we talked about the beginning part of power flow analysis. So we talked about power system operations, power system basics. You will do a bunch of homework using Power Word Simulator to get some hands-on experience. And then, we have some power balance constraints, power control, transmission line limits, overloaded transmission line. We have a load model, which assumes the constant real power and reactive power at the load bus. And we have a generator model. And then now we can do power flow analysis. So, we discussed that the power system is a linear system, and the definition of linear system is when we have two inputs and we have a system, we have outputs. Then when we have two separate inputs and the sum of this input is fed into the system, then the output is just the summation of the original two inputs. So that's the definition of linear system, as you know. So interestingly, if we only have passive components, we can apply this linear superposition principle in analyzing power systems. But actually, because of our assumption of the constant power consumption at the load bus, that is not valid. So power system is actually a nonlinear system. So that's why this power flow analysis is not quite easy. Anyway, let's look at some example. This is a linear power system model where we have only passive elements, resistance only. So we have two voltage sources, and here we want to compute the current at the resistor R3. Then we have two voltage sources. So linear system, so you assume that we have only a voltage source V1 and then compute the current here, and then we assume there is only one voltage source V2 and compute the current here, and just the sum of these two gives you the answer. So that's called superposition principle. And this is what you learned in your basic circuit theory or basic circuit analysis, right? But the thing is that in real power system, again, we have this constant power load, like a factory or building or university. We assume that this huge load consumes like a 10 megawatt of active power and 2 megawatt of reactive power, okay, in a steady state. So because the total power consumption at this load is constant, now this system becomes nonlinear, okay? So this cannot be analyzed using superposition principle, okay? So nonlinear problems can be very difficult to solve and usually require an iterative approach. So today we will discuss Gauss-Seidel method, which is one of the popular iterative method. And then maybe next Tuesday we will discuss Newton-Raphson method. Okay, so what's the problem with nonlinear system? A very simple example, a quadratic equation. F of x is x squared minus 2. If we want to compute the root of this equation, 0, so you see here we have two roots, plus minus square root of 2. Or sometimes if this is the equation x squared plus 2 equals 0, that does not give us a real solution, okay? So this is a simple example of nonlinear system, the quadratic system. And then, let's look at another example. So here, one voltage source, 9 volt, and 1 ohm in the transmission line. And here we assume that the load consumes 18 watts. Okay, so your laptop or your TV consumes 18 watts. Then actually, we assume this load need to consume 18 watts. But in this example, we think this is just purely resistive load. then what is the corresponding resistance of the load? You can compute that using this equation. So the power consumption at the load side is I squared times R. And when this load, the resistance is R, then the current is V over total resistance, so 1 plus R. So this square times R is 18. So you see we have R square. So if you move that term here, this is quadratic equation. And we have two solutions. One solution is when R equals 2, and the other solution is R equals 0.5. If you plug in these two values, you will get the same answer. Right? So another simple example of the nonlinear system. By the way, another question. What is the resistance to achieve maximum power at the load side? What is that? 민재. Yeah, so to give me the number. Yes, when resistance is 1 ohm, then the load consumes the maximum power. You remember that, okay? Maximum power transfer condition is that the impedance of the load is same to the impedance of the line. Actually, if this is impedance, having the complex component, then the conjugate of the line impedance is the condition of maximum power transfer, right? So now we will define a very important concept, which is called admittance matrix, okay? And I will derive this linear equation, I equals Y times B. Actually, that part is described in your textbook, chapter 2, 2.4, but the derivation is not quite kind. So let's do that together. By the way, so here this I equals YV. This is one of the fundamental equation in power system you must remember. And another fundamental thing is the complex power at bus I, okay? You may be confused. Hey, professor, you are talking about the power system is non-linear, but this is a linear equation. Why is that? So I will get back to that point shortly. And this is a vector, okay? So suppose that we have a node like this, and they are connected, like this, like that. And the node index is I here, and this node index is K. Then this is the, okay, here I is actually a vector of, suppose that we have n nodes, and the I sub I is the current injection from node I into the network. This is the injection current, okay? And similarly, VI, yeah, it's obvious. This is the voltage at node I with reference to the ground voltage, okay? So this is same to this one. So 0 is used to the ground node. Then what I want to derive here is that this linear equation. And if you only focus on this i's element here, you see I should be the summation of. By the way, when we have a graph, that kind of graph is a collection of nodes and edges, and each edge or line has the line impedance. Okay, and the inverse of impedance is called admittance, right? So let's say this small y, ik, is the line admittance, between node I and K. Okay? And then what you know is that the current injected into this network, that is I sub I, is the sum from the Kirchhoff current law. This should be same to all the outgoing current, right? So that is for the node which is not equal to I, and YIK, and the voltage difference between these two. So VI minus VK. Everybody agrees with this, right? Then, by the way, so this means K equals from 1 to N, but not equal to I. So this is same to YIK, actually minus VK plus, and same thing here. So this part, so summation K equals YIK and VI. And this part, this is a summation across K. So you put parentheses like this. And then what do you see? Here, this component is a linear summation from K equals 1 to N except I. And when K equals I, we have this part, right? So if you define, now we want to define this admittance, bus admittance matrix, Y bus, simply Y. So Y is Y IK. Then we need to define such that YIK is from here, this should be minus YIK, the admittance between the minus of the admittance of that line, right? And also when K equals I, so II, what should it be? This should be this one, right? Do you see that? Summation of this plus that, right? So, and then if we define this as the summation of K YIK, then using this new notation, we can say this is same to K equals 1 to N YIK VK. Right? What is this? The ith element of current is the linear summation of the voltage. And the matrix notation of that is this one. Right? Any questions about this derivation? Do you agree with this? Why not? Yeah, obvious. Okay. So okay. Then, this is just definition. Remove this part. YII. Okay? Just this is our definition.
모두 I에서 I로 가는 어떤
This is just our definition. Yeah, this is definition, okay? We define like this to make this kind of linear equation. Now, are you okay with this? So, this term is called self-admittance. And the meaning of self-admittance is a summation of all the admittance connected, summation of all the admittance of the buses which are connected to the bus I, including bus I. So we will see shortly that it also has, no, you can easily assume that we have some reactance component here. But actually this node I, we have a ground, Then we have some parasitic capacitance. Okay, so the meaning of this is to sum of all the admittance of the line, including itself. Okay, so in another example, we will see what this means. Okay.
저 위에 것도 definition 거죠?
Yeah, this is also definition. So please don't be confused. The element of admittance matrix, this is off diagonal term. And this is a diagonal term. So the diagonal element is the sum of all the admittance connected to that node, including itself. And yeah. And for the off diagonal term, this is the negative of the admittance of the line.
그리고 로테이션 저게 굉장히 그 엘리멘트
Yeah, the notation, this means that this is a matrix and its i's row and k's column element is this one. Okay, so actually in your textbook and in this slide, they using somewhat confusing notation because to denote the line admittance, they also use the capital Y. So please don't be confused whether that is the admittance of the line or that's the off diagonal element of the admittance bus admittance matrix, Y bus. Okay. So this is an example. This is a general derivation, but in your textbook or in this slide, they have just an example, but yeah, same. So here, this is a Y-bus example. We have 1, 2, 3, 4 buses, and we have generator, load, and the line impedance, Z. And the admittance of this line is the inverse of the impedance, right? And the current injection denoted by I sub I is the current injection from the generator IGI. So for this node, we have generator and load. So it injects current, but this load draws current. So IGI minus IDI is the net current injection into the network. So the sign of the current is the when current is injected into the network, that is a plus. Okay. So, okay. I think we need to refer to this diagram. I want to copy that in this blackboard. Okay. So bus 1, we have a generator, load, and then admittance, and another bus, another load. This is 2, and then this is connected, and the impedance, another bus. This is bus 4, another generator, and then this is connected to bus 3, and load, and another generator, and this is AC. Yeah, this is ZB. 1, 2, 3, 4. We have 4 lines and 4 nodes. Okay. So using KCL at bus 1 here, the injected current is I12 plus I13, and I12 is V1 minus V2 over ZA, and I13 is V1 minus V3 over ZB. And then, so yeah, here this capital is the admittance, which is the inverse of the impedance. Okay. So yeah, YA, YB, okay. and then V1, Y1, YA, YB, and V2, minus YA, and minus YB, V3. Okay, so I1 is this. So we have V1, V2, V3, and this part is the diagonal term, right? When we construct the bus admittance matrix, this is the diagonal term. Because I1, V1, same index. And what do you see? This is the sum of the admittance connected to this line, ZA plus, okay, 1 over ZA, okay, yeah. YA plus YB. Right? So that is here. And for this part, this should be the admittance between line 1 and 2, and put minus sign there. So line 1 and 2, admittance is YA, so minus YA. And here, this is the minus of the admittance between line 1 and 3. 1 and 3 is AB, so minus YB. Okay. Similarly, you can derive Y2, blah, 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 blah. And here again you see, so this index is 2, and this V2, so this is the diagonal, one of the diagonal term. And here, 2, plus 2, it has 3 lines, and the sum of the admittance is YA, YC, YD. So YA, YC, YD. All the parts minus, minus, minus. Okay. So, in this example, the injected current vector and the bus voltage V, and then the bus admittance matrix looks like this. So you see this diagonal term and off diagonal term. And there is one more property I want to mention here. So what do you observe from this bus admittance matrix? Y bus or Y has some property. What is that? Yeah, this is symmetric. No? Minus YA, minus YA, minus YB. That's obvious because YIK equals YKI, right? So that means the element of capital Y, IK, should be equal to the capital Y, KI, okay? The symmetric matrix. Okay, yeah, symmetric matrix. And from now on, we will mostly write capital Y instead of Y bus. And yeah, so maybe later you will get, hopefully, you will get real data with huge number of buses, 4,700 of buses. And then it has bus admittance matrix. And please be careful about the sign of that, okay? So the YKK or YII, that term is called self-admittance. That is called the self-admittance, which is equal to the sum of the admittance of all devices incidence to the bus K. And off-diagonal term, YKL, are equal to the negative of the admittance joining the two buses. Another important part is that in large power systems, like Korea power system has more than 4,000 buses, huge power system. In that case, this bus admittance matrix is sparse. Sparse means most of the terms are 0. The reason is because we have 4,000 number of buses. But one bus is connected to only a few number of buses, like 3, 4, 5, 6, 7, 8, sometimes 10. Okay? So most of the terms are 0. Okay, and the sparsity is the things we want to exploit to compute the power balance equation or to solve optimal power flow, etc. Yeah, the sparsity is key to efficient numerical calculation. And yeah, now I want to talk about this shunt admittance or shunt capacitance. We didn't discuss this before, but this is also important term, so please pay attention to this. Shunt term, such as the equivalent pi line model, only affects the diagonal terms. So let's see what that means. Actually, in the textbook, we skipped chapter 3, 4, 5. Actually, chapter 3, we cover slightly chapter 3, but skipped most of that part. But please remember, this is very important in terms of the transmission line and the parameter of transmission line. And this model is called pi model. Pi. The reason why this is called pi is because this is a bus I, this is a bus J, and then we have a transmission line, and this is ground. Okay, so we have transmission line, this is per phase analysis. In reality, we have 3 lines, but this is per phase analysis, we have only a single line. Then this line has some reactance component, inductance components, so that's why we have YK there, that's coil. Okay? Typically, the transmission line has very little resistance, but some meaningful value of inductance components. Okay, that's YK. Another important part is this one, capacitance. And actually, bus I, transmission line, and this is ground. And we have some tower here, another tower here. This is bus J. Some voltage here, Vi. Another voltage here, Vj. This is 0 volt. This is copper line or aluminum line. The electrons can be charged here, especially in these AC power systems. So there is some parasitic capacitance on this line because electrons can be charged on the line. So there is a huge but thin capacitance element in this line. Okay, but that capacitance is continuous. But using the lumped parameter model, we put all the capacitance into bus I and bus J. So the capacitance component is denoted by YKC for the line K, but this is divided by 2. So half of the capacitance is at bus I, and half of the capacitance is at bus J. Okay? And then there are 3 components: the inductance, capacitance, and capacitance, and the shape is pi, right? So this model is called pi model. And this part and that part is called shunt capacitance. Shunt, the meaning of shunt, the English meaning of shunt. What is the English meaning of shunt? What is that? What? Parallel? Similar, but not exactly. Check it on your own. And so what I want to say is that this capacitance, shunt capacitance, plays a role when the distance of these 2 buses is very far. Okay, so for example, in Korea, the distance between Seoul and Busan is 500 kilometers, right? And the distance between 2 buses is longer than that, roughly more than a few hundred kilometers. then this component and that component is no longer negligible. And especially when we transmit power using AC, then the voltage changes. Actually, in ideal case, this should be 0. But if that capacitance is not negligible, then the voltage change affects the charges stored at this capacitance. Okay, so the power cannot be easily transferred from one node to another node because the power is used to charge or discharge of this capacitance. Okay, so that's why we are using high voltage DC line for long distance transmission. If the distance is more than a few hundred kilometers, then we need to use DC transmission, high voltage DC. So actually the mainland of Korea and Jeju Island is connected by 2 HVDC lines. And in a bigger country like China or United States, the long distance transmission is based on this HVDC. Okay. So when we have this component and that component, then what I want to do here is modeling the shunt capacitance in the Y bus. And the current from I to J, that is I sub Ij, and that is the voltage difference Vi minus Vj times the admittance of line K. And then, but you see, there is a current. So from bus I, one current, the other current. Okay, so that is this part. Okay. So that means Vi and Vi. Originally we have Yk, but you need to put this part here as well. So when you compute bus admittance matrix, you also need to consider this shunt capacitance as well. In ideal case, we do not have this shunt capacitance, but in reality, we have the components. Okay. Yep.
션트 커패시턴스라고 저게 트랜스미션 라인에 있는 부분이
Yes. Parasitic capacitance, 기생 capacitance is a continuous factor, but we are using lumped parameter. Okay? So we assume 2 components at bus I and bus J.
이게 거리가 멀면 멀수록 저게 이제 고려가 된다.
Yes. Yeah, because this line is kind of capacitant. The line itself is a kind of capacitor because electrons can be stored, energy can be stored in this line. So, okay. Yeah. So here we only consider bus I and J, and actually, but there are another bus K, blah blah blah. So I is the sum of all the admittance connected to the bus I plus this one, shunt capacitance. Okay. And Yk is the inverse of the impedance of K in the Rk, obviously. So let's say 2-bus system example. So please don't be confused that this is impedance, line impedance, but this is admittance. Okay. So the line impedance is 0.03 plus J 0.04, and this shunt capacitance is J.1. And then what we want to do is we want to construct this one. So impedance. So just compute I1, the injected current. It's using KCL, V1 minus V2 over Z plus this current, V1 times the admittance, where 1 over z is that. Similarly, you can compute y2, and this is the matrix notation. Okay. Using the y bus, if the voltages are unknown, then we can solve for the current injection. Sorry, if the voltages are known. So yeah, typically this y bus matrix is given. Okay? And if we already know the complex voltage V, then we can compute the current injection at all nodes, right? And actually, yeah, if we know this complex voltage, then everything is determined. Done. Okay? Using this linear equation. Or, similarly, if we know the old injected current at every node, then this voltage, complex voltage at each node is simply computed by computing this inverse of the bus admittance matrix, obviously. But the thing is, okay, don't be confused that when we write Z bus, this is not, the element of Z is not the impedance of the line. This is the inverse of the admittance matrix. Okay? But the name is bus impedance matrix. So please don't be confused. So solving for the bus current. For example, in previous case, we assume a voltage is 1.0 and 0.8 minus. By the way, so here we are using per unit analysis. So the voltage magnitude is normalized by 1. Actually, yeah, the voltage is divided by some base number. So in ideal case, the voltage magnitude is 1.0. And in fact, when you compute the voltage, it slightly changes, like a plus minus 5%, depending on the network conditions. But normally, the value is around, the magnitude of the voltage is around 1.0. So, okay. So, yeah, we know Y bus admittance matrix, and the voltage is like that, and the current injection is computed. So why are we doing this? We know the complex voltage, we know the complex current injection, that we can compute complex power at each bus by simply using this one. Okay? So power system is easy in the sense that you only need to remember this one and this one. So yeah, again, when you compute the complex power at each bus, the sign, when the sign is plus, minus, plus, minus, I'm not sure. So when the sign is positive, I think it means, I don't know, you need to check the meaning of the sign plus or minus. If the plus is the generation, then the minus is the load, but you need to check that. I'm not sure. Anyway, if you compute that, the S1 is this much and S2 is that much. But let's see the example. This example. So this bus 1 is generator bus and bus 2 is the load bus. So at the generator bus, the complex power, actually the active power is positive. And at bus 2, the active power is negative. So again, this is the sign is determined from the injected power. When the sign is plus, that means the power is injected into the network. When the sign is negative, that means it draws the power from the network. Okay? Another example is that here we assume that the current injection is given. Yeah, here the voltage is given, but here the current injection is given. Then you can also compute the complex voltage at each node using the inverse of the bus admittance matrix. Again, you can compute the complex power at each node. Okay, different examples, so different power injection. Yeah. So when you see this, this is positive, this is negative, that means no, the current is injected here and the current is drawn here, right? Okay. Any questions so far? Actually, today's lecture is very important for the rest of chapter 6 and chapter 12. So if you don't understand, read textbook. Okay? Power flow analysis. When analyzing power systems, we know, okay, what's the problem? In analyzing real power system, we know neither the complex voltage nor the complex current injection. So here we assume that, okay, we know the current injection or we know the complex voltage. But in reality, we do not know that. What we know is either the active power and reactive power at the load bus, P, Q at the load bus. Why is that? Because we assume that the load at the bus, at the load, the complex power at the load bus are constant, some number, right? So that gives us the nonlinearity, as I told you. So in real power system, we do not know the complex voltage or complex current, but we know this. And this is the requirement from the load buses. This factory, this building, this university requires this amount of active power and that amount of reactive power. And the generators need to meet this demand, active power demand and reactive power demand. Okay? So this is given. And the generator need to satisfy this demand. So yeah, these numbers are given, and also we assume that at the generator bus, the active power injection and the voltage magnitude is given. This is just set, okay, by the power plant operator. Okay, so well, here I use J for load buses and I use for generator buses. And when we when we analyze the power systems, these four things are given, and then you need to determine the rest of the variables. So actually the variable is, okay, as long as you know this complex voltage of all nodes, everything is done, but we do not know that, okay? So that's why then we need to know, okay, actually, again, sorry. So if we know this complex voltage, then no, we are fine, because using this equation, we can also determine the complex current injection, and then using this one, we can determine the complex power at each node, that everything is done. But what we know is that at this load bus, this at the generator bus, this one, then the remaining variables we need to determine is, okay, there are four variables: the active power, reactive power, and the voltage magnitude, and the angle. These are four variables. These are four variables we need to determine at bus I. Okay, but at the load bus, we only know these two parts. And at the generator bus, we only know these two parts. Okay, so for each bus, half of the variables are unknown. And so that's why we need to solve power balance equation to determine the half of the unknown variables. Okay? But again, they can be solvable. The reason is because, again, as long as we know this complex voltage, everything is determined. And this is complex number. So for each bus, if two values are given, then others can be determined. Right? So this is complex, so real part and imaginary part. So it has two components. So there is a redundant information if you consider all of this. So when half is given, the other half can be determined. Okay. So, okay. Where are we? We are here. When analyzing power systems, we know neither the complex bus voltage nor the complex current injection. Rather, we know the complex power being consumed by the load, this one, and the power being injected by the generators and their voltage magnitudes, this one. Therefore, we cannot directly use Y bus equations. This equation is valid, but we cannot directly use this because only half of this is known. But rather must use power balance equations. Okay, so power balance equations is what? This one. Complex power equation. So that is called power balance equation. So let's derive power balance equation here. From KCL, we know at each bus I in n bus system, the current injection I sub I must be equal to the current that flows into the network. This is same as before. This is slightly, you may think this is obvious, but this is slightly confusing because it requires the definition of I. But we didn't define that. Do you see what I'm saying? You don't know what I'm saying? So forget about it. Or if you want to think about it, just think about it on your own. Okay. So rather than using this notation, we'd better use this or this one. Okay. This is what we derived, and that is written here. Same thing. Yeah, then you can define this I sub ik is this one. But actually, we do not use that. Mathematically, you can define like that, but we do not use that. And the network power injection is, again, SI equals VI conjugate. Power balance equation. So the reason why we start from here is because we assume constant power consumption. So that is given, that SI part will be given to you. And just plug in the definition of I sub I, and this one to there, you have that equation and conjugate, Y conjugate, V conjugate. And that's complex equation, so you can split the real part in imaginary parts. By the way, so this is the element of the bus admittance matrix. This is the real part. This is the imaginary part. And what is the name of G? And what is the name of B? So, okay, yeah. So this corresponds to conductance, and this corresponds to susceptance. But again, originally minus of this is admittance, right? So here, yeah, this is not equal to the admittance of the line between I and K. This is the minus of the admittance between I and K. Anyway, so we have that real and imaginary part, voltage, magnitude, and phase, and the phase angle difference is like that, and this is Euler formula. So just plug in complex power, plug in, and then Vi is Vi times e to the j zeta I. And this is Vk, magnitude of that, and minus zeta k. So just plug in and then you will get this one. Just straightforward. If you are not sure, just plug in and just solve this by your hands. And then it has derivation, and still we have this complex part using Euler formula from here. And GB that comes from the bus admittance matrix, and the real part and imaginary part, real power and reactive power. Okay, so here the variable P, Q, voltage magnitude, and the phase angle. Actually, zeta I minus zeta k, zeta I minus zeta k. So the variable, we have these 4 variables. And when there are n nodes, the total number of variables is 4 times n. Right? And, and the number of equations is 2 times n. Right? So 2 times n equation and 4 times of n variable, but half of the variable will be given to you. Half at the load bus and half at the generator bus. So the half of the variable, 2 times n variable, can be determined by solving this nonlinear equation. Why is it nonlinear equation? Because this is variable, but we have the product of that two, sometimes the square of the voltage magnitude. Okay. By the way, if you have this function, x and y are scalar, we can consider this kind of function. A simple function. Is it convex function or not? Is it convex? Check it. Yeah, this is not a convex function. You may think this is convex function, but this is not a convex function. Okay. Anyway, so you need to solve it. You need to solve power balance equation. Okay, so power flow requires iterative solution. In the power flow, we assume we know SI at the load bus and the bus admittance matrix. Then we would like to solve for the values VI, and that VI is complex, so voltage magnitude and phase angle at the load bus. Okay, and for the generator bus, we need to compute the reactive power and the voltage angle. Okay, so how can we solve that? Again, go back to this complex power definition and just plug in, and we have that. And let's do the iterative approach. So to do the iteration, our first try is very simple, and that method is called Gauss iteration or Jacobi iteration. And that method is named after a very famous man in history. So you may think that is awesome, but it's very simple. How does it work? The intuition is we just want to this kind of simple equation, x equals h of x. H is some function. So just for simplicity, let's assume x is scalar. But actually this x should be a vector in our case. But if x is scalar and if function h is given, what is the meaning of the solution of this equation? The meaning of that, what is that? The meaning of the solution of that equation is this one. Fixed point. What is fixed point? The solution, the solution of x times h of x. Let's say this star. Star is conjugate, so underbar. Yeah, let's say this underbar is the solution of that. Then x underbar that satisfies this equation is called fixed point of this function h. The reason is because when x underbar is plugged into this function, it gives the same number as itself. The input and output are same. So if you think this is x, and then this is y equals x, and then let's say this is a function h of x. Then this is the solution of, right? Then how can we determine this point? Very simple. Start from some number. Like we need to use iteration. So let's start from some initial value x0, and then evaluate that function value, right? And then apply that value into this function again, and then you will get this value, and apply this value to that function again. Then you will get this value, and it converges to this point. Okay, very simple. Or if you start here from x0, you start from here and evaluate the function value here, then this, and then again applying this function h, then you will get this value. Am I correct? Yeah, correct. And then it will converge to that point. So if this function h has this kind of nice property, applying this Gauss iteration gives you the fixed point of the function. Okay? But the reality is that what if the function is like this? This is h of x. This is another fixed point. But if you apply this iteration, Gauss iteration, and you start from here, x0. You start from here, x0. Then evaluate the function, gives you this value, and it goes to that point. Oh, it has another fixed point. This is not what I intended. So what I want to tell you is that we go to another direction, so we cannot converge to this point. Okay, so this Gauss iteration does not always work. Sometimes it works, but sometimes it does not converge to the value. But anyway, this kind of equation, the fixed point concept, is very general in mathematical analysis. And so this theorem tells you that Brouwer's fixed point theorem. Brouwer's fixed point theorem is very fundamental theorem in real analysis. 고등미적분, you took advanced calculus. Did you learn Brouwer's fixed point theorem or not? So Brouwer's fixed point theorem says that if you have a function or mapping T, which is from R to the N to the R to the N. So this is a vector function, takes the vector as an input, and the output is also vector. And the domain and range are a compact set. You didn't learn compact set, but there is a concept of compact set. Domain, range are a compact set, and this function T is a continuous function. Then there is at least one fixed point. That is called Brouwer's fixed point theorem. And this analogy is something like this. Suppose that the molecule is just a point. Okay? And this is a nice cocktail. And okay, in a steady state, every molecule, the point molecule, is at some position, and you just then pick up this cocktail and shake it, and put it down, and wait until it becomes steady state. Then there is at least one point where the position does not change before and after shaking this cocktail. That is the concept of Brouwer's fixed point theorem. Very clear, right? I borrowed this slide from myself. This slide was in my faculty talk at Sogang University 12 years ago. Okay? To explaining the concept of optimal user association of mobile systems. So in that case, I don't want to talk about that, but if you are curious about that, you can check my paper, which was cited more than 400 times. What was that? I forgot the name of the paper. User association. Distribute alpha optimal user association and load balancing of wireless networks, or something like that. Okay. So, how can we solve this iteration? Very simple, as I already explained here. No, starting from here, the example is f(h) of x is square root x plus 1, and start from some initial point and evaluate this again and again and again. Okay, so just plug in and plug in again and plug in again and plug in. So xv plus 1 is simply computed 1 plus square root xv. Just do this iteration. And sometimes it converges, okay, to the fixed point, but not always. And we also need to have some stopping criteria. And if the difference between the iteration is very small, like delta xv is defined as the difference between these two values, and the difference is less than epsilon, when this is a scalar, you can use the just absolute value. And if this is a vector, we need to use some kind of norm, either L2 norm or infinite norm. So if the norm of the vector is less than some epsilon, then you can stop. So then how can we apply these to solve power balance equation? We need to modify this equation in the form of Vi equals h of Vi, but just rearranging the terms. Okay? So again, the fundamental equation, just plug in this I, this one, to that, blah, 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 blah. And take the conjugate of that, and you get this one. Actually, this is redundant. And then divide both sides by Vi conjugate, and you have that. And then when k equals I, yi, vi, when k is not equal to I, you have that part. And then, okay, so we have vi here, so divide both sides by y sub ii, like this. So this minus that part, divide by y, ii, give you that one. Now you see, vi is a function of vi. X is a function of h of x. So vi is a function of vi. So just plug in and do the iteration. Yeah, hiv. Ooh. hiv is given like that. So, okay, so just do the iteration. From some initial value, do the iteration. And it converges sometimes. And using some stopping criteria, you get the solution. This announcement is not relevant to you, but I put this slide to emphasize that you need to solve a lot of homework problems. Okay? So the students at UIUC, University of Illinois at Urbana-Champaign, homework 10, this number of problems. Okay, so you need to solve a similar number of problems to get some hands-on experience. And there are some more interesting slides. I think the author of the textbook put these slides so that the students must study hard. Otherwise, this kind of thing can happen. So this is the failure of wind blade. The height of this wind blade is 140 foot. That is 42 meters high. And then one of the blade is broken. And so the company, Solgen Energy, lost the share of the market by 39%, almost 40% after this accident. So I check the stock price of this company. If you are curious, check it on your own. But also there is some kind of disclaimer here. Vestas, another big, actually maybe number one, wind turbine company, and Siemens turbines have also failed. I don't know, so I just borrowed this slide. Another failure. Thermal power plant can fail as well. At Illinois, 2007, this turbine exploded. Okay, so ESS can explode. Wind turbine can be broken. Thermal power plant can explode. What else? Transformer can fail as well. Okay. So actually a rocket can explode. You know that. Space shuttle exploded in 1985. I saw that when I was an elementary school student, 4th grade. I'm not joking. So, in TV, way in the United States, there is a space shuttle, Columbia, something like that, was launched. It goes high, 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 and then exploded. Okay. So let me stop here. Any questions?